Good evening and welcome to tonight's nanoTalks. My name is Joel and I'll be guiding you through the October nanoTalks. In October and November, we always like to host nanoTalks about the Nobel Prizes, and today our plan was to bring you one nanotalk about the historical perspectives of the Nobel Prizes and one nanotalk on the Nobel Prize in Physics this year. Unfortunately, Leander isn't feeling too well today and can't be with us this evening, so his talk on the historical perspective on why Nobel Prizes are given for specific research will be delayed by a few days, but we will upload it to our YouTube channel. So if you want to make sure to catch it, subscribe and click the bell and you will be notified once his talk is online as well. But we still have a very cool program for you tonight with Iris de Vries talks on the Nobel Prize in Physics in 2021. But before we go more into the topic, I'd like to quickly introduce REACH, the organization behind the nanotalks, and give you a bit of an overview of how this evening will go. So, REACH, we are a young Swiss-based think tank, and we want to build a world where science and society work together. How do we want to do this? Well, we have 4 core activities that I'll quickly want to mention. One, REACH is running a blog where young scientists write articles and explain topics to a broader audience. We have a podcast in German called Weiter Wissen. We have evening events, like the one you're attending at the moment. So everything from small gatherings to big exhibitions that we're organizing to reach more people and talk about different scientific topics. And REACH is working on making policy recommendations, mostly through our Francini project. If you're interested in any of those activities, we're really a grassroots organization, so follow us, stay informed, or get involved. You can click on the link in the description of this video to get to the nanotalk page, sign up to our newsletter to hear more about the next upcoming nanotalks or general REACH events. You can become active in any of the activities I described before, or join our over 300 members all over Switzerland, in Zurich, Bern, Basel, Lausanne, now also a few in Geneva, in St. Gallen. Become active or just follow us, go to our website, www.reach.ch, or follow us on Twitter, Facebook, LinkedIn, and so on. But back to why we are here today. We're here for the nanotalks. Nanotalks means we'll get nice, interesting talks from young scientists, but it also means you get a chance to interact and to ask questions. At any point during those talks, you can go to Slido and enter the code nano-oct. You'll also find this information in the description of the video. Any questions you post there, I will ask Iris afterwards in the Q&A, and we'll have a chance to hear answers on all the questions that are of interest to you. And that wraps up this short introduction. As I mentioned in the beginning, in case someone missed it, unfortunately, Leander can't be with us today because he's not feeling too well, but we will record his talk soon and upload it to YouTube afterwards. So if you want to make sure that you'll get notified when his talk is online, subscribe to our channel, click the bell to get a notification. And with that, it's time to get into the actual content. And it is my pleasure to introduce Iris de Vries. Iris is a PhD candidate at the Institute for Atmospheric and Climate Research at the ETH Zurich. And she also really likes to bike. And with that, Iris, the stage is yours to tell us more about this year's Nobel Prize in Physics and about climate modeling.
Thanks for the introduction. Hi, everyone. Thanks a lot for attending these talks. So I was also expecting to have a historical perspective talk before my talk, but luckily I also put some history in my talk, so it won't be completely historyless today. But as explained by Joel, I'm going to zoom in on one particular Nobel Prize, namely the Nobel Prize in Physics, which was awarded partially to two climate scientists this year. And I think, as you all know, we are flooded with climate model results in all sorts of media presently, but we don't see what actually underlies the enormous amount of climate information that we get every day. So which events in history led to this point? Why did we ever even decide to make those climate models? And what did it take to get to the state of the art that we have now? It wasn't all as intentional and targeted as it may seem. One could even say that the development of climate models was to a large extent circumstantial. So I will take you through some key points in history that, in retrospect, shaped the development of climate science as we know it. Then I would like to give you some insights from the inside of climate science in the present, and I hope to leave you with some food for thought for the future. So let's start with the history. For a long time, until about halfway the 20th century, we can distinguish two branches of research. On the one hand, there are circulation models, and those were concerned with atmospheric airflows. And on the other hand, we had radiative transfer models, and these addressed the global average balance between incoming solar energy and outgoing long-wave radiation. Only after these two branches merged, climate change studies as we do them now became possible. So in the following, I will single out some events in both branches of research, and I will end this history shortly after the merging of both science branches, which marks the birth of climate change science as we know it. So first, the circulation models. The main initial motivation for modeling the atmosphere in general was weather prediction. The foundation for numerical weather prediction were laid by Wilhelm Bjerknes in 1900, who suggested that the entire atmosphere and also the ocean can be described by 7 primitive differential equations. The idea then to use these equations to predict weather systematically on a grid was brought up by Louis Richardson in 1922. He developed this idea and he actually managed to create a prediction system on a grid, but individually it took him 6 weeks to predict 8 hours of weather. So to speed this up, his ideal vision was to have a computer factory. And with computer, he then referred to humans, and he envisioned that 64,000 human computers would be sitting in a factory, computing in parallel to create worldwide weather predictions ahead of time on a grid. This, of course, didn't happen, but his daydream was developed further, and grid-based weather prediction development led to an actual realization of the computer factory, but of course not with human computers, but with actual computers. And in 1950, then the ENIAC, the Electronic Numerical Integrator and Computer in Pennsylvania, produces the first numerical forecasts for local weather. But at that time, still the computation time is equal to the forecast time. But already in 1958, the technology of computations enabled local weather forecasts that could predict the local weather 5 days ahead of time. During this development of the local weather forecasts using computers, John von Neumann, a famous mathematician who also started the group that performed these first numerical weather forecasts, took on the challenge of simulating the circulation of the whole global atmosphere. And in order to do so, he pushed for the establishment of a Center for Research on General Circulation. The center, which is now known as the Geophysical Fluid Dynamics Laboratory, the GFDL, produced the first global circulation model in 1956, which was really just aimed at understanding how the circulation works. And the success or the production of this model might be considered the split of weather modeling and climate modeling, as now with these models, the space and the time scales are a lot larger and they go far beyond the space and time scales of short-term local weather forecasts. In the same year that the first GCM, General Circulation Model, was produced, Sukuro Manabe, the first Nobel laureate that we'll encounter today, joined the GFDL. And there he also contributed to the development of these general circulation models. So that brings us to the point where we have working circulation models. And at the same time, but largely disconnected from these circulation model developments, radiative transfer models were used to understand the energy balance of the Earth. And these models could develop separately because radiative transfer models are simple 1D models that don't need to take into account the circulation. So we go back again to 1900, or even a little bit before 1900. And at that time, motivated by the wish to understand how large fluctuations in the climate, such as ice ages, could exist, Svante Arrhenius investigated how the radiation balance of the Earth is affected by the presence of certain gases in the atmosphere. And in the paper shown here, you see that he specifically looks into carbonic acid, which is CO2. And what is also quite remarkable is that already in this paper, the term hothouse or greenhouse to describe the effect of the atmosphere on energy trapping on Earth was already coined. So that's already very early. Arrhenius asks himself a question if CO2, carbonic acid, could be responsible for these large climate fluctuations in the past out of scientific curiosity. And he calculates, using a very simple model, that a doubling or 2.5 times more CO2 would give a temperature rise of around 8 degrees in the Arctic. And given the current climate models, that was not even so far off. But of course, Arrhenius is not yet aware of the actual effects of human emitted CO2. But it doesn't take long until people start realizing that. Already very, very early on in 1938, radiative transfer modelers realized that the release of CO2 in the atmosphere by human activity will have an impact on the temperature. So Guy Callender is the first one to do an actual climate change detection study, where he shows that theoretical calculations about CO2-induced warming correspond to what we see in observations. Later it's argued whether this could actually be called a detection study, but now we can say that this was the first detection of climate change. And after Callender, there were several more papers that looked into the effect of CO2 emitted by humans on temperature. And unsurprisingly, with the suggestion of human-caused temperature changes, also skepticism about these human-caused changes was born. And Fritz Müller was a scientist from Germany. He visited Manabe at the GFDL. And at that time, he published this paper that questions the effect of CO2 on temperature, based on the idea that water vapor in clouds also could have caused temperature fluctuations that we're seeing. The uncertainties and the incomplete understanding about how CO2 affects temperature is a very strong motivation, especially also this paper, a very strong motivation for Manabe to further investigate the effects of CO2 on temperature. So we could maybe say that this early climate skeptic paper might have played a very essential role in the advancement of climate science. I do need to mention that Fritz Müller was not a climate skeptic himself. It's just this paper that was skeptical. Hence, Suko Manabe also contributed to radiative transfer models and not only to the general circulation models. His and Weatherhold's efforts to clear up this contradiction or the disagreement about the role of CO2 on temperature led to what is now considered one of the most influential climate change papers. So these two men developed a realistic vertical atmosphere model that takes into account the effect of temperature on water vapor. And using that, they estimate that temperature rise due to a doubling of the CO2 concentration should be around 2.5 degrees. And this estimate is still very well within the range of the current estimates we have with highly complex models. Their motivation for making this physically correct radiative transfer model is to include it now in general circulation models to better simulate the climate. Even though most of this research is still curiosity driven, by now the research on the effects of CO2 on temperature have started to alarm scientists. And in 1970, scientists write a report called, I'm saving some energy here, the light turns off automatically. I knew that was going to happen. So in 1972, there's a report written by scientists called The Effect of the Study of Man's Impact on Climate. And then also the United Nations start an environmental program, and there's political attention for the issue of climate change, and that further pushes the advancement of knowledge. An essential step in advancing the knowledge and in better simulating climate change is the merging of these parallel research lines into one by the inclusion of radiative transfer models into general circulation models. Manabe is one of the drivers behind the development of these general circulation models, which integrate CO2 effects. And he's then also the first one to run a general circulation model with doubling of CO2. And the results here show a much more complete picture of the effects of CO2, as they can tell us that higher latitudes show more warming after doubling of CO2 than low latitudes, for example. And they can also tell us more about the latitudinal, so north to south pattern of precipitation changes due to CO2 increases. The development of climate models continues, and more components are added to make them more accurate. On this slide here on the top, we see the atmospheric model, including radiative transfer. And then the bottom shows a next generation model where a very important component, namely the ocean, was added to the circulation model. And Klaus Hasselmann, the second Nobel laureate, contributed significantly to the representation of oceans and variability on different timescales in climate models. So now we can say that climate models include all the components of the Earth system, and more specific studies can be done that examine the effects of human influence on many aspects of climate. At this point, the independent and the joint history of circulation and radiative transfer modeling have generated enough results to spark more need for action on climate change. And this then leads to the establishment of the IPCC in 1988. And to date, the IPCC is still the most trusted and comprehensive body when it comes to climate change. And you could also say that from here on, the primary use of climate models is the simulation and the projections of human-induced climate change. And in fact, the latest IPCC report came out only a few weeks ago. And with this latest IPCC report, we reached the present of climate change science. So let's zoom out a bit again. And we can say then that although all of this may have started as an endeavor to forecast the near future local weather and to understand the Earth system, the course of events and the circumstances led to the current present, where we have climate models that simulate climate change. Of course, this global timeline did not include all of the advances that have been made over the history of climate modeling. And the models have developed a lot since the first couple GCM. So for example, now models include more physical processes, representations are improved, there's more level of detail, and also the spatial and the temporal resolution of the models is a lot higher. So the question you may ask is, what did all of this then culminate in? Where did 100 years of unplanned and planned model development bring us? Currently, we have a very large amount of very complex and very lengthy Earth system models, and they all use different ways of simulating Earth systems components, here represented by these circles, and their mutual interactions. And these are just six models, but there are many more. And all of these models are employed to simulate climate change in a coordinated way, to feed into these IPCC reports that summarize the state of the climate. And every cycle, about 7 years, the IPCC organizes a coupled model intercomparison project, so-called CMIP. And the runs for the latest IPCC report of all these climate models generated on the order of 30,000 petabytes of data. And for those of you who don't have an idea of how much that is equal to about 60 million pretty expensive laptop memories. And now you might ask, why is this necessary? If Manabe could already simulate the climate with such a simple computer, actually, and such a simple model, why do we then need so many models and so much data? And how do we use all this data to actually learn things about climate change? Well, one of the main questions, or you could say the main question in climate change research, is how do we find the signal in the noise? And how do we know that this signal is because of human influence? In this figure, you see 30 possible temperature trends over the US in the second half of the 20th century. And all of these temperature trends, so that's 50-year increases in temperature, or 50-year changes in temperature, all of these trends are equally likely. And as you can see, some of them show cooling and others show warming. And there's no way of saying which one is more correct. They're all equally correct. And this natural variability means that in order to reliably determine climate change effects, we need reliable uncertainty estimates. And that then gives rise to the need to simulate as many climates as we can with very many different models that might have different dependencies or different inaccuracies. And besides allowing many simulations, another very important aspect of all these climate models is that we can control the environment. We can do experiments with the climate, so to say, and therefore we can turn on and off certain human effects and extract the isolated response of the climate to that specific effect. These features combined, so the ability to run a lot of simulations and the ability to turn forcings on and off, allows us to determine the fingerprint of a certain forcing relative to the natural variability in the system. So that's illustrated by these two plots. The average temperature trends on the left show the effective change in temperature, just averaged. But the regions that here show a very large temperature trend are also the regions where there are a lot of variations in temperature from year to year or from decade to decade. Therefore, we create a detection metric shown here on the right, derived from all those model runs. And this detection metric then represents where we expect the signal due to the forcing we're interested in to be strongest relative to the natural climate variability. And then trying to detect this fingerprint of expected climate change in observations allows us to estimate the human influence or the forcing's influence on the actual present climate reliably. And then according to this plot, for example, we can see that the effect of human forcing is unequivocally present in every single annual temperature observation from 1999 onwards, as then we go beyond the natural variability range. And Klaus Hasselmann, the Nobel laureate, contributed very significantly to this technique, this detection and attribution technique. So this brings us then to a summary of the history up to now. And I think that our ability to reliably assess climate change depends on the possibility to run millions of simulations with different forcings, and that would not have been possible had it not been for these exploratory researchers that wanted to understand ice ages, that had dreams about forecasting, and that were curious to understand the natural system. Many of these early researchers were not aware that their work would become as vital as it is today. And in my view, the history of climate modeling shows that unplanned research driven by curiosity and a wish to understand, in combination with the circumstances and awareness of the world around you, can lead to these massively important discoveries, which can have a very large impact. And that then maybe also brings me to an important question. As we may start research without a plan, we, on the way, stumble upon a problem. And the question is it then our duty as researchers to address it? The goal of Manabe was to understand the climate system, and then he found climate change. The goal of Hasselmann was to reliably detect human-induced climate change, and he did. And now we are here. We have climate change, and we know that it's caused by humans. And the difficult question is then, what is the next goal of climate science? And I'm going to leave you with this question. Thanks a lot for your attention, and I hope you enjoyed it.
Thanks a lot, Iris, for this very interesting presentation about climate models. If anyone has questions to ask to Iris, you should see the credentials to log in to Slido with code nano-oct, where you can post questions, and I'll then ask Iris those questions, and we'll now have a bit of a discussion and a Q&A about this. Maybe one first question from Slido, which is you've now shown us this history of climate modeling, and a lot of it took place even with the Nobel laureates in the 60s and 70s, if I saw this correctly. And the question was, when was the actual research done that the Nobel Prize was given out for now? Is this continuous research, or can you point to specific points where they did something?
I think it's generally continuous. What you see is that Manabe was involved in, basically from the beginning, he was involved in almost every step of climate model development. I think they describe in the Nobel Prize the motivation for giving them the Nobel Prize is their contributions to reliably simulating the climate and assessing climate change or human effects on the climate. So I would think that for Manabe, it's mostly the fundamental development of climate models in which it was essential. And Klaus Hasselmann did a lot, very detailed work on variability, and that was a bit later. And then also this detection that I showed at the end. And I think, yeah, Klaus Hasselmann was definitely later in the history than Manabe. Manabe was at the very beginning. But generally, a Nobel Prize is an oeuvre prize over the whole scientific career.
Fascinating. Also fascinating. I mean, you really focused on their work now, on like also their contributions. I'm sure there are thousands and thousands of people who must have done work on climate modeling. Is it like for someone doing research in a field that got a Nobel Prize, does it like feel like the field has been recognized, or how do you like take this into account when people in the field get these kind of prizes?
Yeah, I do think so. I do have to say that I feel like the modeler, the people that do the modeling and the people that do the analysis were maybe the same people way back, but I feel like now that's a little bit more disconnected. Of course, we very much depend on the modelers, but I don't feel like I can take any credit for model development. But it definitely feels like recognition of the importance of the field. I think it's maybe also a slight political statement of the Nobel Committee.
Yeah, okay. Maybe jumping on this, then on maybe it's a slightly political statement. What kind of impact do you think can a Nobel Prize have?
I think a lot. Yeah. Definitely, because I feel like I don't know if everyone feels that way, but this year, or very recently, there was the IPCC report that stirred up a lot of dust, even though I then have to say it didn't say anything new, but it's good that people were shocked by it. IPCC report, then there was the Nobel Prize. Yeah, maybe that's only two things, but I feel like there's a lot of sort of clogged attention now at the same time for climate change, and I think that's definitely going to have an effect on just the presence in people's heads, that it's something to think about, and maybe then also the political opinions, right, and the support for climate change measures and voting behavior. Yeah, I do think it can have an impact. I think there was a different prize, but when Obama won the Nobel Peace Prize, that was also had quite some societal impact.
Well, let's hope for that. There's another question from Slido, which is a bit on, again, like how many people are in this field. And the question is, how many researchers have reproduced these models that are shown here? And how many of them agree with the findings? Like, is it you all find the same, or like different kind of predictions come up depending on who models it?
So it really depends on what we are looking at. So I invite you to read the IPCC report. It has about 3,000 pages. No, but there they simulate a lot of different things, of course. And the nice thing about these IPCC reports and this CMIP runs, the Model Intercomparison Project, is that all the models are exactly tuned the same, or not tuned, but their inputs are exactly the same. So they specify exactly what to put into the models, and therefore they can really assess what the confidence is on certain results. And it really differs per quantity. So if we look at temperature, basically all the models say exactly the same. And then you have this very high confidence level that there is human effect and like how big the effect is. I do have to say that this last run of models was quite different from the run before, in the sense that doubling of CO2 led to more warming in some models than it did in previous runs. So actually the uncertainty on how much warming results from doubling in CO2, that's called the climate sensitivity, that's become maybe a little bit larger again. And if you look at how they simulate the sea ice retreat or the precipitation changes, things that depend also spatially, like where does it change more, where does it change less, there's definitely a range between the models that can be large or small, but there's definitely not any model that says everything's going to cool down and there won't be any more heavy precipitation events. Like the sign is quite certain. And if you read these IPCC reports, most of the changes, there are these headline statements, and there you can see how high the confidence is, and that also indicates whether many models agree. And it's mostly it's quite uncontroversial at the moment.
So the models all agree on direction. How much do they agree, or you said there's a bit of uncertainty depending on how it's modeled on maybe magnitude. Like, can you describe that a bit? Of like, you said early on that early models predicted 2.5 degrees of warming, and you said like that is close to what we now predict. Is it like from 0 to 4, or are we like 1.8 to 2.5?
From 2 to 2.5 to 4. I mean, I have a slide. I can show you this here. This is a slide that shows all the predictions basically throughout history. So it also here shows Arrhenius. So this earliest one, he was a bit on the high side with his range. But this gray bar that represents the range that most models are in.
Can you quickly introduce how we need to read this?
Sorry. So I cut it up because it was too long a figure. But the x-axis shows the climate sensitivity, and that is the equilibrium climate sensitivity. So that's the new equilibrium temperature of the Earth after a doubling of CO2. So it takes some time to get there, and then it will plateau there. And that's globally average. So that doesn't mean, it still means that it will be more warming at the Arctic and our latitudes and less warming in the tropics. But here we see basically from 1896 to now what all the models and theories have estimated as equilibrium climate sensitivity. And you can see some outliers, mostly to the high end. But this is generally the range. And as said, Manabe, so the first actual climate model, was here. So that's pretty within the range.
There's another question in the chat, maybe a bit on like what goes into these models, and the question is, isn't it a bit narrow to just focus on the CO2? Aren't there other factors that influence this as well, and maybe how much of this goes into the models?
All of it. Of course, not all of it is correct. Some are correct. That's maybe not. We don't know everything. So there are two main problems. One is we can't simulate everything that we know because maybe the scales are too small, so we can't put it in the models. And another thing is some things we just don't know. But not only CO2 goes into the models, also all other sorts of emissions. So that's methane from permafrost thawing or from cows, but also aerosols and very specific chemical compositions of aerosols. So you would have sulfate gas aerosols, but also soot, soot from, for example, forest fires, that are also simulated. Volcanic eruptions only in history. We don't predict future volcanic eruptions, but those effects from history are also in there. And then the IPCC always employs these different scenarios. They're now called the shared socioeconomic pathways. And they're not predictions, but they are possible what-if scenarios. And these also include developments in the socioeconomic sphere that then influence, maybe we have a decrease in the amount of aerosols, but an increase in CO2 or something else. So there's all sorts of different weightings of different effects that are all included in these models. And it's so also clouds and really we try to put everything we can in the models.
So a lot of things go into those models, but the models all seem to agree on the direction. Now, you are doing your PhD on some part of climate modeling, right?
Yeah, on the effect,
Where do you think, like, given that those models seem to agree this well, like, what else can those models tell you, and where do we need, like, would they need to be developed? What new could they bring?
Yeah, so that's a question I do ask myself. We know the general idea. We don't know the general idea of everything. So there's one thing that is always brought up. Those are aerosol cloud feedbacks. So the effects of clouds on the climate and how clouds react to climate change and also to different aerosols, so pollution chemistry. That's something that we're very uncertain about, and the possible effects go from minus something to plus something. So we don't even know the sign. So for example, increased accuracy on that is something that could definitely still be achieved, but also global climate models, because they need to simulate so many years over so many locations, they have relatively coarse spatial resolutions, which means that they can't resolve certain processes, and that makes them less accurate. So pushing for higher resolution, that's something that is very much done also now, would probably also change our ability to really zoom in locally and see the regional effects of climate change. And I think maybe that doesn't solve anything, but it would help in adapting, right? In trying to prevent damage that we can't anymore, or deal with damage that we can't anymore prevent. Really. So I think that's still a role for climate models. Yeah.
Very fascinating. Another question. You mentioned in your talk that those models or can also be used to like try and estimate the attribution of like how much of it is human based and how much can be natural processes. That is on a general level, right? On like on the whole system. Or is this can this also be done on a per event of like if we have a flood, can we use these kind of models to answer the question, was this flood caused by climate change?
Yeah, so that there is definitely a very active branch of climate science that does that. It's called world weather attribution. It's kind of a conglomerate. And it's not possible to say this event was caused by climate change. That's never possible. But what is possible is to sort of assess the probability of the event happening without climate change and the probability now with climate change. And in my view, that provides very solid evidence. If now such an event is a lot more likely, that there has been a very strong contribution of climate change to the occurrence of this event. And in that sense, there is a possibility to attribute the fraction, that's called the fraction of attributable risk. So,
Thanks for that explanation. Maybe one last question to wrap it up. Let's go a bit broader here. What inspired you to get into this kind of research and to do climate modeling? What for you was the driving force to pursue this type of research?
This maybe sounds very Messiah syndrome, but for me it was really the fact that there is a serious problem and that I could contribute to some extent to maybe making that a little bit less bad. So I think the climate system is very interesting, and I also am fascinated by everything about it without climate change. But I think the main motivation was that there is something that has to happen, or at least if I can contribute in some way to reducing the suffering and the inequality of climate change. That's sort of the overarching motivation. And then just my daily work is also very much motivated by just the fascination for the processes and for the science.
Very cool. Those are very noble aspirations. So thanks for all the work you do there in the modeling, and thanks especially for taking time tonight to tell the audience more about climate modeling and how we came to this point where we can do this kind of climate modeling. I really want to thank you for your time, and to the audience, before you leave, just one last little reminder. So let me switch over to this. For one, we originally planned to have Leander give a talk tonight about a historical perspective on why Nobel Prizes are given out for specific topics. Given that he was sick today, he will record this talk and will upload it to our YouTube channel soon. So subscribe and you'll see this very soon. And then in a month from now, on the 25th of November, we'll have the next round of nanoTalks. This time it will be about the Nobel Prize in Medicine and Physiology, all about sensing temperature, touch and pain. And the second one on the Nobel Prize in Economics. the so-called credibility revolution in economics. I hope you will join us again for these nanoTalks. And with that, well, thanks a lot, Iris, for joining us today, and have a nice evening, everyone.